All right.
Yeah. And she kind of ended up being in the hospital. Her parents came in or whatever. And he was so she was the second kid. Oh my goodness, one second. See you connected. Did you sign already? Yeah. And now it's not even loading like this page. You know the page to log in. Yeah. Why is this all such a big?
Okay, well, I'll just do it the other way.
How do you get out of it?
Okay, questions before I get going?
How do you do count corners?
How do I what? How do I count the corners?
I think I got
Oh,
one, but you can
all right. I guess I haven't. The thing was due, right? So I can safely put up a solution.
Yes. Yeah. I mean, that's tragic.
One of them, like, how you test it? That's how you test it.
This was which homework? 22, 24? 24, she says.
They just made really small names. I don't know why. And just count rows for each one.
All right, let's see how it counted.
And you can use
Corners.
you count out.
Okay, so here's how I counted corners. Well, can you turn one of the lights off, please? Thanks. So, yeah, maybe the other one, huh? Thanks. So, it says count the number of corners in the maze. So I go through all of the rows and all of the columns, and I ask if at ij there is a corner, and if so, I increment the counter, and then I return the total of the counter.
What's your is corner?
Aha! So what I want to point out here, that what I did, first of all, is I didn't ask you to write is corner, right?
Yeah.
But it is a good idea to introduce these extra helper functions, because otherwise you're going to have some really big and complicated code that's sitting here. And so introducing these helper functions is something that I highly recommend. And I figure the way to get people to realize that is to not tell you. So if you try to do it without a helper function, then you would now see the wisdom of this. So that's something that I generally like to do if something gets to be too complicated to do it all at once, to come up with this helper function. So let's now look at the helper function is corner. So I need to find out whether something is a corner, and so if it doesn't have if it's not empty, then we say it's not a corner. And now I do something else that's kind of useful, is I say, well, I have these other functions that I can make use of, so I'm going to call free neighbors, which gives me all of the directions that contain free neighbors. Now that of course assumes that you have implemented free neighbors, otherwise that's kind of tough. So free neighbors gives me a set of directions, north, east, south, west. If I don't get exactly 2, it can't be a corner, right? Because I want one in this and one like that's kind of sticking out. And so if I don't get 2, then it's not a corner. And so now now I have to find out, well, fine, I have 2 now, otherwise I wouldn't have survived. And is it a corner? Well, my difficulty is that I get this array list of strings, and I don't know in which order I get them. I don't want east-west, and I don't want north-south. Any of the 4 other possibilities, I'm okay. So I need to check for east-west and for north-south. And I don't really know whether east is going to be the first one in the set or the second one, because they could have been delivered to me in random order. I don't really know how this thing was implemented. So I check, does it contain an E? And if so, then it better not contain a W. because otherwise it would be a straight line. If it contains an n, on the other hand, then it better contain an s, because otherwise it would be a straight line. Done. So this is easy if you don't view this as a separate problem from the rest of the problems, if you're willing to call one of the other problems. And of course, fair game. Implemented the other, so I might as well make good use of it. Was I nice? Did I ask it after the other one? Or did I ask it before the... did I put it before or after three neighbors?
Oh, after.
I was nice. All right.
But I didn't see. I don't think we had it
No,
before.
no, no. You had to have the, first of all, I expected you to have the, I hope. I didn't expect. I hoped you had the insight to write is corner.
No, is there a method of is corner inside?
I hope that you would have the initiative to write that method on your own.
Oh.
Ah, yes.
So used to filling in the blanks for that entire
Yes, the when it
class.
says dot, 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 it means give it your best. And in this case, that means to come up with a method yourself. That is the best way of doing it.
I didn't even see it is corner with dot, dot, dot.
There is no is corner. I asked you to come up with it, to invent it.
Where do you ask us
You didn't.
I didn't explicitly say, it was just my hope that you would.
Can I put it inside column?
No. If you got it successfully done, you must have had a bit of a mess of code in here, right? So if you have a solution that has this, and then inside here it has like 10 lines of code or whatever, that's fine. But isn't this better? Ah. And that's fine, right? The thing is, if I tell students and say, you know, you should do this and this and this, there's so many different things that one doesn't think about it. But when you first see something that you did in a way that maybe you felt was unsatisfactory, and then you see a better way, it's easier to learn that way. So just next time. There's no penalty if you didn't do it this way. But it is, as we progress, it's my expectation that now you know about methods, now you know how to call them, you know how to write them. So once in a while, you should be able to implement your own helper method. So such a thing, the technical term for this is it's a helper method. It's not one that the problem description asks for, but boy, it's useful to have it. Okay, other questions? Anything else that you want to see? Anything else that you found ugly, that you have a solution but you're not happy with it, where you might want to see an answer?
Is count free space in rows, right?
Okay, that one is actually pretty easy.
Yeah, does that mean like count all the free space in one row?
Yes.
Or all the spaces in a row?
All the well, I guess that means the same thing. So here's the code. So we fix the row, we go through all the possible columns, and if there's a space,
Count them all.
yeah, so it just counts all the spaces. So in my solution for free spaces, I've said, since I already know how to count all the free spaces in a row, I might as well make hay of that, and so I just iterate through all of the rows and call that method. Again, it's easier to call the methods than to re-implement that stuff. Did anyone do this? Okay. Anything else? See if there's anyone that... No, I think these... Okay, the other one where I made a helper method, just because I can't figure stuff like this out, is when you want to compute the neighbor in a direction like north or south or east or west, there's like, you have to go up or you have to go down, you have to go left or you have to go right. So I used a couple of helper methods that I wrote where I say, if you want to go south or north, you have to add 1 or minus 1 to the row. If you want to go east or west, you have to add 1 or minus 1 to the column. So you may want to have a look at that. That's kind of a useful trick. These things are going to happen over and over again. In 46B, you're going to be seeing mazes for a number of different things because they're kind of useful examples. So it's probably a good investment to look at this solution and see what you can glean from it. Other questions? All right, let me go through what I want to say about the lecture, and then I have a few things to say on how that applies to the next homework assignment. So the basic topic of sections 8.1 and section 8.1 is how do you come up with classes. So we've now left the lands of loops and arrays, and we're going to go back to classes and objects for the remainder of the semester. And so the problem that we want to face is you have some kind of a program that you're supposed to write that solves some kind of problem, and that problem the description of that problem generally talks about real life things. And in fact, to make it a little bit more real, let me show you the homework assignment. So this is, and it's kind of longer, so I broke it up into 3 deliverables. Oh,
Wonderful SJSU wireless.
well, the thing is, I'm actually on the wire. I don't even know why it bothers me. All right. So in this assignment, you will implement a program that determines the winner in an instant runoff election. So what they do in you know the standard kind of election, people cast ballots, and whoever gets the majority is, of course, the winner. What happens if no one gets the majority? I mean, it won't happen so much in a presidential election, but it might happen like in a mayor's election in San Francisco, where there were, I think, 15 people running for mayor.
Oakland had it too.
And yeah, exactly. Oakland had
Whitney
it.
Houston there.
Okay, that's a good question. So the standard approach is you have a runoff. The top 2 vote getters run against each other. And that has a disadvantage because it makes it means for people in the first round, they're usually better off getting something like 26% of the vote or something like that, enough that they get, say there are 4 candidates, that they need to go enough to get into runoff, but they don't need to get enough to actually get a majority, and so they're more likely to become more extreme, more radical. And you don't believe it? Have a look at the Republican primaries. Right? These guys are not going to run on the same platforms in the general. Whoever wins is not going to run on that platform in the general election as they're doing right now. Right now, they want to make sure that they get everyone who has strong feelings about this to vote, and that's enough to push them into the first or second place. And so the voters then decided in San Francisco, and I experimented also in Oakland a while ago, to change that. So now that instead of just voting, so then what happens actually, and this happens all the time, is the first 2 people are strongly liked by, say, 25, 26, 27% of the people. Each of them is absolutely despised by almost 75% of the people. One of the 2 will win, and then you have someone who's fairly radical, who most of the voters do not agree with. So then they changed to the system where they said instead of having a voter just express who they like best, how about telling who they like second best and who they like third best? And so they take that into consideration. The entire system is a little bit complex. So what happened in Oakland is that there were a couple of people who did not make it because some people liked them a lot of people didn't like them at all. And so it was really kind of bland, not very interesting person, who everyone kind of liked second best, got elected. Now people complain, but if you ask me, why did they vote for him as second best if they hate him? Well, you don't vote for someone as second best if you hate him. So maybe people didn't understand the voting system. And maybe the concept of best, second best, third best is too much for the poor voters of the fair city of Oakland. In San Francisco, it does seem to work just fine, and so people have figured this out. The voters seem to have figured it out. The candidates seem to have figured it out because the candidate who did win asked people to say, give me your first, second, or third vote. And it worked. That guy got a whole bunch of first votes, not enough to push him over the edge, but he got enough second or third votes from people who seemed to think that he was an acceptable candidate, that that was all right. And now we have someone who, may not be the one who everyone loves, but at least everyone did at one point say, that one is kind of okay. The way they sold it to the voters, by the way, was to say it saves money because the runoffs cost money. A runoff election in a city like San Francisco costs $5 million. And by having an instant runoff, you basically say, well, let's just pretend the runoff was today. If your favorite candidate was eliminated, then who would you vote for? And just tell us who that person would be. And so it's a reasonable system, but it is a little bit complex because the way they do it is, as you'll see, they take the ballots that belong to candidates that had little success, and they take the least successful ones. They then transfer their second choices to the candidates who were so named, and they keep doing that until someone gets the majority. So that's the voting system. So now let's say we have such our task is to implement such a voting system, as in fact is your task. And when you want to do this in an object-oriented way, you now need to come up with classes that have something to do with the problem domain. So you've seen a bunch of classes like points and rectangles and ellipses. I think it's fair to say that none of them are going to be useful in our situation, or bank accounts and cash registers, and they aren't going to be very useful. So what class might be useful? Give me a class that you think might be useful to implement homework 26, whatever, the next one.
Election.
Excellent. Election, right? That might be a useful class. And so that's in fact what you do. You say, maybe that's useful, so we'll just make a note of it and say, election sounds promising. What else? Usually you need some number of classes that collaborate with each other. Yeah?
How about a vote count?
Okay, so he has a vote count class. Okay, we'll write it down and we'll go through it. What else? Give me a couple more ideas. Give me an idea. A bad one.
Add.
What's that?
Add a ballot or something.
Okay, so he has add a ballot. Okay, give me an idea. An idea, any idea? No. That never happens during voting.
Get rid of the ballot?
Just think, no, you're too focused on what he was saying, which was actually a terrible idea, and I'll demolish it. So think of the whole process. What goes on in the voting, because we kind of have to count the ballots and determine the winner and choose between candidates. Okay, we have.
Majority.
What's that?
Like a majority.
So he says majority. There is that kind of sounds like might be possible. Okay, give me another one. I'm not saying it's good. I'm just saying it's an
Candidate.
Okay. Okay, so let's stop it here. Now let's look at some of these things. And I want to demonstrate that this is harder than you think. That it's not something that comes necessarily very naturally to people. So let's see which of these I think are good classes. Generally, the rule of thumb is that, and it'll be on the next slide, but I'll write it on here, that a class should be a noun that's in the problem description. So I love candidate. That to me sounds like a perfect class. You know, we have candidates in the selection. And a candidate has a name, and the name must somehow appear on the ballot. And so that sounds, and then candidates aggregate votes, right? A candidate could remember how many people voted for him or her. And so it looks like this is something that would make a useful object. So I think that one is worth keeping. How about add a ballot? What's wrong with add a ballot? That sounds weird, right? And if you look at the rule of thumb, it's not a noun, right? I mean, you would say, how many add a ballots did you meet today, right? So it's not a noun. So, but where is the noun? Ah, thank you. So ballot is a perfectly good noun, right? And it kind of makes sense that how does the voting system work? I mean, it has to read in what's on each of these ballots, right? They get scanned in some way, hopefully reflecting the voter's intent. And so you would imagine that when we simulate it, we're going to have like a text file with with the various choices, and we could read each line into an object of type ballot. And particularly with this more complicated election, where a ballot, you discard the votes for those candidates who no longer matter. Ballot works out great. How about vote count?
Would it be okay if you added ER?
Yeah, you could maybe have a vote counter, and then the question is, sometimes these classes can be useful, and the question is, in this case, is that kind of worth it? Because it probably the counting of the votes happens somewhere in a simple loop, and you probably don't need a whole class for it. So generally, we kind of keep a class for a state that we want to stick around for a while, whereas for an action, we turn that more into a method. So and this kind of sounds more like an action. So because it's an action, I'm going to say we should probably find out who can do the vote counting. And maybe the election can't count the votes. So one would probably eliminate like this. And similarly with majority, that's more like an attribute. I could say that the winner makes sense to me. But the winner is an object. It's an instance of candidate. One of the candidates is going to be the winner. So I think majority is probably not going to make it a good class. So this, I've given you the outline for this in the homework, and the classes that I've used is election, ballot, and candidate. So the good news is that they did kind of come up through this process of discussion. So that's basically how one does these things. Now in a beginning class, you're not really expected to be terribly good at this process. There's a whole another class, CS 151, where you're going to go through this in more detail. But you should know the basics that there is a process for discovering classes, and it's just not totally trivial. So that's the one thing that I want you to know. Well, here, now this is the problem description. Thank you. Okay, that was number one. Number two. There are a couple of rules that one uses when one looks at classes to see whether they're well designed, or whether one should maybe break them up into two classes or move responsibilities from one class to another. So one of them is the single concept rule, where we say that a class should represent, it should do one thing and only one thing. So for example, we will want to separate the ballot from the candidate because they do different things. You could maybe come up with a design where they're somehow unified. So here's a bit of a more subtle example. Here I have a class that's this cash register from somewhere much, much earlier, and it has this enter payment method where I enter the number of dollars and so on. And then it's also concerned about how the value of each of the coins. And we did it at the time in this way because we didn't want to use multiple classes. We just want to use one class. But now when you look at it, there's two concerns in here. One is to maintain the balance on how much the customer is supposed to pay. And then there's the independent question of what's a coin worth, which will be different in different countries, for example. In Europe, they'll have different coins. And the way things are going, they may be having many more coins soon than the United States. And so these two concerns, totaling up payments, what's a coin worth, are both together in this class. And so one says it's not cohesive. So what's the solution? The solution would be to say, well, we're dealing here with some concept, and that concept should get another class. So let's do that. There's this concept of a coin lurking here, and a coin has a value. And then one can, over here, instead of entering all of these numbers, one could say, you know, one adds a coin. Or maybe a list of coins. And then at that point, the cash register would no longer have to worry what's the value of a quarter or of a nickel, because it would simply ask the coin, what are you worth? And so then this one would be removed from the cash register. So the coin would be cohesive, because all it deals with, what's the value of this coin? The cash register would be cohesive. All it would say is, here I have these coins, I find out what they're worth, and then I add it to the payment. And that's a better reorganization of it. So once in a while, you'll find students come up with classes that are not cohesive, and typically you can tell from the name of the class. Like if it's called Homework 24, chances are that that puts everything together, when in fact it might be better to say we have ballots and we have elections and we have candidates. And so in that case I would say that was not a cohesive class. You would have been better off separating the responsibility. All right, now let's say we were good and we separated our responsibilities. Then we get into another issue. Now we end up having more classes. Yeah. And so in this case we had the cash register and the coin class, and the homework we have the voter, the ballot and the candidate and all of that. Once you have more classes, then you start wondering about the dependencies between the classes. And the reason you care about dependencies is if you have too many dependencies, it's hard to maintain the system. You get kind of spaghetti dependencies. So what's dependency mean? We write dependency with a picture like this, and it means that this class here knows that this class exists. Because it uses it in some way. Maybe it uses coin parameters in this case, or it has a collection of coins inside, or whatever. So a cash register knows that coins exist. And that's right. Does a coin know that a cash register exists? From this picture, we would say no, because there's no arrow in the other way around. And that probably makes sense, because a coin class is just a simple thing that has the value of the coin, and maybe the year it was minted or some such thing. But it has no need to know anything about cash registers. That's good. So the fact that there's not an arrow in the other direction is nice. So there's no arrow here, and that's good. The fewer arrows you have, the more easily the system can be maintained. So let's have a quick look at how this looks like in our voting system. We have an election. Ballot and candidate. And let's see, does a ballot have to know about candidates? So if you think of what happens with the ballot is presented to the voter. The voter checks off their choices. Does the ballot have to know about candidates? Yeah. Kind of, because it has to should list them all, right, so that the voter can see it. So we would have an arrow this way. Does a candidate have to know about ballots? No. They don't. Because for all you know, the candidates might be elected in a different way, by acclamation or by random choice or whatever. So, and that's in fact when you look at the outlines in the homework, the candidate knows nothing about ballots. And that's good. Does the election need to know about ballots? The election is the thing that determines the winner. Kind of, right? Because otherwise it would be very difficult. It's not for it to do its job. Does the election need to know about candidates? Because it pronounces the winner, and the winner is a candidate, so it needs to use them in some way. And now, as it turns out, the ballots don't know that they are in an election. There's nothing in the ballot that makes use of any election objects, and the candidates also don't know that they are in an election. And that's nice. So that way, that the election object doesn't have to be propagated to these. So it's still a fairly simple set of dependencies. There's 6 possible dependencies. We only have 3 of them, and that's considerable. So those are the only 2 concepts that I want to get out of these 2 sections. Number 1, how to find classes with the noun and the problem description rule. There are other ways of finding classes, but that's the simplest one and gets you a long way. And number 2 is to recognize dependencies between classes. Now there's one dependency that the book makes a big deal about, and I guess it is kind of a useful example. Oh yeah, so here, bad, good. That's kind of self-explanatory. So the one dependency that that we often run into is the dependency with input-output. So let's say I have if you go back to the good old class bank account. And remember, it had a method get balance, returns the balance. And now suppose I change that into print balance, where it says system.out.println balance. That might actually be easier, because there's a whole bunch of programs that we had where we added money to the bank account, and then we wanted to print the balance. What did we have to do? We had to call get balance. We had to feed that to system.out.println. Why not just have a method print balance? So the thinking is that this would be bad because it makes a coupling between bank account and the class print stream. The system.out object is a print stream object. So it would make this coupling, and we would think that would be bad. So we don't like to do it. So the general rule of thumb is that unless you have to, you should not put system out or system in inside other classes. And why is that? When you do that, you make your classes less usable. Now in CS1, it may not be such a big deal, but let's imagine you do an actual voting system. You know how these systems work. They have like a bunch of consoles that are maybe connected to a central computer, and they have like some displays and stuff. They don't have a system.out. Like when you do any kind of embedded system where you have like the computers inside your car does not have system.out. Right? There's no place in the car where system.out would appear. And so it's generally considered a good idea to not put input-output directly into these classes. And so in fact, when you look at the classes that I have, the candidate, the ballot, and the election, they don't know anything about system in, system.out. Only there's the one class that ties it all together. They then know about reading and writing. So that's something to watch out for. We'll see this more again in the 151 course. But I want to plant the idea in your head that you kind of don't want to read and write inside most classes. You want to localize the reading and writing into one small part of your program. All right, that's what I have. So we're in for the lab. This is lab 11A and B. Alright, so we have a group of 4 activity. Let's see that we have enough groups of 4. It seems to be a little thin today. And so that one is straightforward. You're given a problem description, and I want you to come up with the classes that you would use to implement the system. You know, try your best coming up with the classes. Some of you will come up with funny ones, and that's okay. And then make a UML diagram. That's that kind of diagram that I just showed you with the classes and the dependencies. That shows those dependencies. And you could do it on a sheet of paper. In fact, I recommend you do it on a sheet of paper. And then to turn it in, you could take that sheet of paper and stuff it in your computer and see if it arrives on the other end. Or you can take a photo of it or whatever. Or if you enjoy this kind of thing, there's this nifty tool where you can put in a text description and it makes the diagram. See if you like it. So part B, again as a group of 4, I want you to have a look at this program and talk about dependencies. Alright, let's do that and regroup and see how we do. So we have enough groups of 4?
We'll have to find a different two other people. Just like I need to. Oh no, it was just we haven't signed it. Like I just because season 2 doesn't, so I just made a team. And like I'm getting my friends.
So what was the update last night about?
What?
The update last night.
Yeah, the season 2 just started. You can make ranked teams now like this, like I just made, and you and your friends get it or whatever, and then when you join ranked team, you join it as a team, and then like your team's ELO is what it shows. It's cool because you can join with your team,
And then just whoever's on at the time will. Yeah, you have to be in a group to do it, or is it just...
Yeah. Because like if you look in regular queue, there's normal, but then there's ranked teams.
Oh, that's cool.
And like you can be on as many teams as you want. So like I'll have like my like SJSU team with people I know SJSU, and then I'll have my other circle.
Then you have like the good players and the other circle.
Yeah, something like that. And then I'll go from either. How do I get to the labs again? Yeah, that's what I used to do. But I had to like delete all the purpose and stuff.
I'll find out.
We can move.
They're going to work. You're going to work with them then?
Okay.
The party's better because you get more space.
Yeah.
How much time do we have?
I'll be either the
Library.
Mike Deli.
Yeah.
You don't speak out.
So why don't you show up? I'll be sure to have someone.
Okay. I'll show you.
Then you have, yeah, then I can have some captain or I can give you some.
How do you spell?
Yeah, without.
Yes, I do. It's like you read my mind.
And those are all individual documents. Decide what how to add that, like check in, check out. What calls with it.
Another person is going gold plus.
And then the other one is what the other.
So we need to make a Google diagram and see the picture of it. So we have to track people and what they have. Do you guys have a camera?
Yeah.
Yeah, I will say it's part of ID. People who are borrowing.
So I guess it's fine.
I guess you need to copy it.
I'll just say items.
And it checks, it's gonna check if it's in or out.
No, catalog would be your items.
So we have to check out this.
Do you want to have something as items, just class items, and then class catalog?
So, fine, we can do that. Or no, let's.
How many collected times have you acted? No. Saying that they should be very,
I guess.
Just trying to show us how to.
Are we just getting the picture? I mean, are they all just branching out from the right? Or are they
First one, you know, the first one.
I
Pretty much, I don't on that.
Well,
If it's
for inventory, if you have,
yeah, the girl. It says ask like the inventory.
reservations are probably.
we have to look into the inventory.
What is it?
Reserve something.